determine whether or not there's, which one is bigger and which one is smaller. And the error that we have on this depends on the accuracy of our measuring device. So with discrete, you're moving up by whole numbers, but with this, we could move up by 1/16 or 1/32 of an inch, or micrometers if we had a device that was finely enough graduated. So the units here, the error here depends on the accuracy of your measuring device, not just counting ability. Yeah?
No, it was continuous or categorical?
This would be continuous. I probably said categorical, but I meant continuous. Sorry, thanks. All right, I want to get back here for a minute. Okay. The type of data you have is going to affect the kind of statistical test that you can do. We'll talk about that a little bit more in another lab where we have different kinds of data that you can look at with different kinds of tests. For categorical data or discrete data, so counts of things or measurements of things, what you use is a t-test. And I know that many of you have had some experience with the t-test. What the t-test is going to allow us to do is it's going to we're going to be able to look at the signal we've got, which is the difference between our two averages, and consider also the amount of variation around that point. And what that looks like here is, here's a distribution. So here's the mean of my black distribution. Here's the mean of my red distribution. Are they different?
What's the X line?
So the X is my, whatever I measured, my measured variable. My Y is the number of observations. So are they different?
No.
We've covered all the bases, I think. Yes, no, we don't know. And the answer is you really don't know just by looking at it, because you've got all of this variation. If it looked like this, so if there was no variation, and this was the average for the red group, and this was the average for the black group, that's unequivocal. Yeah, those are different numbers. But we've got variation. That's the noise in the data. This is where the passionate part of the passionate t-test comes in. You've got noise in the data, so we need to be able to filter out that noise. And the way we do it is by doing this thing called the t-test. The formula for the t-test, what you're going to do is calculate something called t-observed. And t-observed is going to be the signal, which is the difference between my two means, the mean of group A and my mean of group B. And we want to also divide that signal by the amount of noise or overlap that we've got. And one measure of overlap is variance. So I'm going to say, okay, variance of group A and variance of group B, I want that in my equation. But variance is related to sample size, so I need to account for sample size differences. And variance is a squared value, so I need to take the square root of that so that I can account for that squaring in calculating, that I have in calculating variance. So the t-observed is going to be the mean of group A minus the mean of group B divided by the square root of the variance of group A divided by the sample size of group A plus the variance of group B divided by the sample size of group B.
How does this relate to the standard deviation?
The square root of the variance is the standard deviation.
Okay, cool.
Yeah. And then the standard deviation divided by the square root of the sample size is standard error. They're all related.
Okay.
Yeah. let's do some calculating with Excel and see how this can work. So what I'd like you to do is open up an Excel file. If you need a laptop, let me know, I can get you one, or yours is not charged. Open up an Excel file, and let me give you a dummy file to work on, or some numbers to work on. Come on.
Where is my? Just open any Excel file.
Okay.
Yeah, just open any Excel.
Just go to Excel and open up a fresh workbook. And save it and call it T-Test Calculator. I've got my numbers here, so I'm good. Okay. So I'm going to put my cursor in a cell, and I'm just going to call it group A. And then the next one will be group B. And then I want mean, variance, and sample size. And then my numbers for group A would be 23 point, whoops, where'd you go? Oh, stop it. Oh. All right, so what I'm going to do now is in a box, just write, T observe, and I'm going to move over to the box next to it. And we want to calculate a formula, so we're going to have Excel do that, so we tell it to equal sign. And you want to open up a parentheses, and you're going to click in the cell that's got the mean for group A, minus the mean for group B. Close your parenthesis. And then we're going to divide that by, oh, wait a minute, the square root, SQRT. And the variance divided by the sample size. Variance divided by sample size. Yeah, if you need to move around so that it's easier to see the board.
Oh my. I think I can see it.
All right, the other thing we need to do is figure out degrees of freedom. And so my degrees of freedom, again, is my sample size for group 1 plus, my sample size for group 1 plus the, oh, stop it, equals.
No, it's not this. I think it's not numbers, we'll go back and figure it out too. And then include the after the
Well, that's not right.
You went to E52.
Oh,
I'll give it a subpar rating.
there, that's that.
Hey, what is it?
So what this is the sample size from group A plus the sample size from group B minus 2. That's my degrees of freedom for the t-test.
And is that because you minus 1?
The other thing I have to decide is whether this is a one-tailed or a two-tailed t-test. This in fact is some clammy data, so this is baseline and this is t equals 0. So I would expect to see more non-moving clammy after the pH drop. So that tells me it's a one-tailed test. I'm going to do a one-tailed test here. If I just wanted to know that these were different, I would be doing a two-tailed test. Yeah,
So for the one tail, it's not like you're saying which one I'm looking for, but it's like you just have no clue which directions were they looking for.
for a two-tailed test, you
That's
don't know
two-tailed,
which
yeah.
direction. Yeah. All right. Now, we've done a calculation. We've come up with a number. How do we know whether or not we have a significant relationship? If I go back to my formula here, if my two means are really different, so that I've got a big signal, and I don't have a lot of overlap, such as when I have data that looks something like this, is my t-observed going to be a big number or a little number? It's going to be a big number. I'm going to have a large signal and low amounts of variance. If my variation is very large and my means are somewhat close together, am I going to have a big number or a small number for my t-observed? I'm going to have a small number. So if t-observed is really big, then I can say that these are significant. And if t-observed is really small, I say that they're not significantly different. People who have more time than we have figured out how big t has to be for any degrees of freedom or probability for tailoredness. So this is a t-test table here. You have one in your lab notebook on page 32. The way you use this table, so if you've got your notebook, or your lab manual, turn to page 32. The way you use this table is you look at whether you figure out the row and the column that you're interested in. So the two columns up here at the top, or the two rows rather up here at the top, one is the probability if it's a two-tailed test, the other is your level of probability if it's a one-tailed test. So you decide if you're doing a one-tailed or a two-tailed test. We're doing a one-tailed test, so we're going to look at, oops, Mary. We're going to look at this column, which is our probability of 0.05. So that gives me all those probabilities. You then look at the
Let's see.
Gesundheit. You then look at the degrees of freedom, which row corresponds with the degrees of freedom. So that's 9 degrees of freedom here. I look at the intersection of those rows and columns, and I see a t-value of 1.833. Now the t-value I calculated was negative 0.88 something, right? But that, I got that negative only because I chose that group B would be the one with the bigger number. So what I'm going to do is take the absolute value of this. So I'll forget the negative number, take the absolute value. My t observed is 8.89565. It's bigger than that number. I'm going to reject the null hypothesis. So if t observed greater than or equal to t crit, we call the t value out of the table the t critical. We reject null. I can say that those means are significantly different. With a probability of 0.05. I have a 5% chance that I'm wrong. Now, in fact, what I can do is I can keep looking at this row until I find a probability where my t observed is less than my t critical. So if I go all the way out here, 4.781, my t observed is still bigger than that t critical, which means my probability is less than 0.0005, 5 times in 10,000. I'm going to be wrong. That's pretty good. Those are very different averages. Suppose I got a t observed of 3 for my same degrees of freedom. I could say, okay, I can reject the null hypothesis with a probability of 0.05, 0.025, 0.01, but not 0.005. And what I would report would be the 0.01. So the lowest probability that I can report and still say that the means are significantly different. If my t observed value was 1.5, I could not reject my null hypothesis. I would have to say that those are not significant. Excel will do a t-test. There's a t-test function in Excel. The problem with using it is it doesn't give you the t observed. It only reports the probability. And I want to see the t observed because then I know if you've done the calculation correctly. So the spreadsheet that you just set up, if you save that, call it t-test calculator. Whenever you have to calculate a t-test for this class or for 140, you just have to plug in the right values for the mean, the variance, and the sample size, and the answer will pop out for you. So you only have to set up that big formula once. Georgia?
So we just use the formula that.
Yeah, so let me, maybe I'll show you here. If I go back to my formula, I need new batteries here. There we go. If I go back to this, if you save this and just call it something like t-test out calculator, then when you've got a group of numbers, you just replace these values with those numbers. So suppose I've done my data analysis for, I don't know, something, paclitaxel. Now I want to do the data analysis for cyclohexamide. I just go in here, I get the right numbers in.
Oh, that's so handy.
Yeah.
Probably what?
I just wrote the number.
And then it all just falls out. So this is essentially what a statistical package will do for you. Underneath what you see if you're using SPSS or R or JMP or anything like that is essentially an Excel spreadsheet, which is just doing the manipulations. What's different is how you tell it to do the manipulations. I know that a lot of people here, or some people here have taken statistics or are taking statistics. There are multiple statistics courses on campus. Bio offers one, Biology 211. Psych offers one, Math offers one, Econ offers one. They're all using different packages of software. We're using Excel because that's the one thing that I know that everybody has access to. And the learning curve for Excel is not as steep as the learning curve for some of the other things. So I'm going to ask you to do, for this particular class, do your data analysis in Excel, even if you can use a different stats package, because then I can evaluate the work that you're doing. It just makes it easier for me. If you're a Mac person and you use numbers, see if you can convert it to Excel. I can't open numbers on my computer. All right, so this is the t-test. Let me see if there was anything else I wanted to say about the t-test before we go on. All right. While you were talking about the dog project, the dog columns, I handed out a sheet to everybody. Even though we've done a lot to clean up the data it's still a big data set. So that's some tips that we've put together for manipulating, working around a large data set. One of the things, we have done the sorting for you, but at some point in the future, you're going to need to know how to sort data. So there's a tab, the data tab on your version of Excel, and that will let you sort the data. You can sort the data in multiple different ways with a single sort. So when we sorted the data, we sorted by treatment, whether it was a baseline, T equals 0, toxin or control, and then also sorted by time. So we can do a two-day sort. Use colors or lines to make visible divisions. That's really helpful. The other thing that I do when I'm working with a large data set is I will, somewhere in my working file, I will set up the information about what rows my data is in for each group. And then I can just check to make sure I've always highlighted the correct data. Or actually what I don't do is I don't highlight. I just type in the cell values. It's faster for me. You might find it useful if you have columns or rows that you're not using, just make them hide. Highlight them, right-click them, select hide, they'll go away. Then you can navigate your spreadsheet easier. When you want them to come back, you just highlight where the column used to be, right-click, and you unhide, and the column comes back. So that's a nice way to do that. And you can freeze panes so you can see the headers. So that way, as you're scrolling down through 200 rows of data, you can always see what the top headers were. There's some other ones on there, and I can show you those as you start getting to work on them. We've done that. Okay. Last thing, then we'll do our microscope quiz, and then we'll turn you loose to work on data. These are some data similar to what you collected with the toxin being colchicine. This is from a pilot study that we did. And when I graph these data, I have baseline, time equals 0, and I can't talk about toxin treatment for these two groups, right? Because they haven't been exposed yet to toxin. But then down here, 10, 20, 30, 40, 50, 60, I do have to keep straight whether I've got colchicine and control. So what I wanted to do was to fool Excel so that it didn't give me meaningless bars on this part. So what I did was set up my graphing file using a table like this. So I have what's going to be my x-axis labels here, baseline t equals 0, 10, 20, 30, 40, 50, 60. I then have the mean, the variance, the sample size, and the standard error for baseline, and I put that into that cell, and I make everything else a 0. I then have my mean, variance, sample size, standard error for t equals 0, that goes below the t equals 0 column, everything else is 0. Do the same thing for all of my time points. So set up the Colchester time points here and the control time points here. Then when I graph the data, what I tell Excel to do is that I have 4 data series. I have one data series which is baseline, one which is t equals 0, one which is Colchester, and one which is control. And when Excel plots that, it then says, oh, baseline. I put, the average is about 23, and then the average for all of these was 0, so I just plot 0 points. That means Excel thinks there's something there, but there really isn't. Same thing for t equals 0, same thing for all of these. So what you can do is force Excel not to put in extraneous columns. Otherwise, what it's going to want to do is to put in, it'll duplicate these columns, which it's hard to see the patterns in the data that way. So that's something that we can help you set up when you're ready to do that. All right, we've covered the first 4 months of a statistics course. Let's take 5 minutes. Kevin and I will get microscopes in here, set them up on your bench, and we can do the microscope quiz. That will take 20 minutes, and then when you're done the microscope quiz, you can spend the rest of the time getting started on your data analysis. At least get the t-tests done today.
Do you have how you set up the 4 series?
I certainly can. Yep. All right. Go get a drink, walk around. See if it's sunny.
It's not sunny, it's hourly outside. Oh, it's a workout. Good, I just started with this. Hey, I'm going with my music. Let's go with my
Okay.
You made it.
That's because it's red.
Oh, you can turn off the.